So this is the SG Brown Meridian Gyro Compass, manufactured in 2005. Really easy to use. The display panel on the front's only got 6 buttons. Not really worried about the alarm or the power on button. You can adjust the display brightness with these. The latitude has to be input, and you can use up and down to set your latitude. Same with speed. And although this is a north-seeking gyro compass, as with all gyro compasses, you need to set in your latitude manually. Unless you have the optional input of a GPS unit, which this one will take, and that will automatically keep the latitude and the speed updated in the unit, so you don't have to worry about it. But if you are using it manually and you don't have the GPS facility, then latitude and speed corrections or inputs must be made into this unit regularly. I just want to show it in its raw form. This is quite a lot of friction there. In the Z-axis, the Y-axis, again lots of friction, and then the X-axis. So the unit itself is suspended in this cast steel gimbal set, really heavy duty, lots of weight. The whole thing is really heavy. And if I start this side, you can see this is a weight here. Got little tiny weights at the side here. Underneath, on the X-axis, there's loads of weight. This is one of the main weights. This is what keeps it sort of horizontal via gravity. There's this adjustment pin here. It's threaded so you can adjust it in and out. I guess that's a balancing mechanism. The flywheel itself is actually in here. It's absolutely tiny. If you can see that, better. It's about 2 inches, and that's with a casing on it. So the actual flywheel itself is less than 2 inches in diameter. If you want to compare that to the super precision gyro, you can see that. The super precision gyro, I measured it at about 53 millimeters diameter. So this is actually smaller. The flywheel in here is smaller than the super precision gyro. So it just goes to show that you don't need a very big flywheel to move all of this heavy mass. And it's quite a long way from its center as well, especially this side when I come round to it. See that the flywheel is at the back here. So this is what they call the damper, big heavy weight, and this is top heavy. If you look underneath, it tapers. It's this thing here. It's really thin here as well. You know, the depth of it this way, whereas here it's what, nearly an inch thick, 3/4 of an inch at least. So I'll just get into the insides. See the little bubble level there? Incidentally, that never seems to be in the middle when it's running, for some strange reason. You've got these pick-off coils here, loads of connectors. Got connectors down here. So inside this box here, there are accelerometers, torquers I believe, all sending signals to the control board, so you can actually monitor them signals, which I do intend to do. But this damper here, what they say this is for, is the gyro as it's seeking north will have a natural tendency to sort of move like this, but obviously much slower than what I'm showing here. And they're saying that the ellipse that it traces out, the major axis of the ellipse and the minor axis of the ellipse are proportional. So if you reduce the minor axis magnitude, it also decreases the major axis magnitude, and it makes this ellipse become ever decreasing until it settles on north. That's the theory behind it. That's what this damper's for. During north seeking though, from what I've seen, if it does do that, it is unnoticeable. Down at the bottom there's a motor, the azimuth motor. You can just see the top of it just poking through there, and that's housed within this sort of casing here. You see all the wires in the back there. And then the motor itself is down there. One thing I can't find in the manual is what the RPM is of the flywheel. It's the only thing I can't find. In general, the manual's pretty good. It gives circuit diagrams, detailed electronics circuit diagrams. It gives you the operating theory behind this, which to my mind doesn't really explain anything. It explains what it does, but not why it does it. Why north? What's so special about north? But yes, these weights apparently have a large contribution to what and how the gyro compass works. These weights give it the pendulous effect to keep the flywheel horizontal all the time, which is the principle of how these things work. Keep the flywheel spin axis horizontal, should I say. So all the outputs and inputs from the actual gyro itself are outputted to here, which then connects into this first PCB board. Just position the light better for you. There's a first layer there at the back, just behind the gyro compass. Lots and lots of electronics. And then there's another board in front. Again, lots more electronics. And then there's this output board at the back here. So all these green connectors are what we would connect into if we wanted to get the output signals out of this and sort of analyse them on the laptop. There's rows and rows of them. You see there's lots and lots of different output signals you can get from all the axes pick-offs. And then you obviously feed the cables through these glands at the back. Looks like somebody's already had one here. And this one's just the power supply going in that somebody's adapted inside down here. So finally, on the other side of the unit, You can see down at the bottom there's another circuit board. And at the top here, there are some dip switches, which I'm not touching. And there are some pots there. And this is a 60-way test connector. And that you can actually access that via the this removable panel and the dip switches and the pots. So next I'm going to show a video sped up of this thing actually seeking north with the case removed, so we can actually see what the gyro is doing. Okay, so the unit started. And in this instance, the gyro flywheel, or the gyro axis, is facing west of north. So you'll see the y-axis start to rise just to find its level, and then initially it starts turning counterclockwise, only very slightly, before then moving clockwise to find its north position, and you'll notice it overshoots slightly as well, and has to come back. This process took approximately 46 minutes. And if I scrub back and forth quickly, you see how the y-axis hardly seems to move. So this is another test with the gyro axis flywheel, or the spin axis, facing east of north. And if I scrub forward, you'll see it starts moving counterclockwise straight away. Again, it overshoots and has to come back on itself. And if I scrub back and forth quickly again, you'll see that you can hardly see any movement in the y-axis. I often find these things easier to visualize when using a globe. So I'm going to stick my super precision gyroscope just here in the UK. Doesn't matter which way it's orientated at this point. We all know that the rigidity in space property is the assumption that the Earth spins west to east, and the gyro wants to maintain rigidity in space. So to an observer in the UK here, it's gone clockwise. You see it's turning clockwise. Always, in the northern hemisphere, no matter where, it's going to want to turn clockwise. That's the premise. Okay? It doesn't matter if the flywheel is spinning. It doesn't matter if the flywheel is spinning that way. You'll still want to be rigid in space. Or if it's spinning the opposite way, if you turn it round and it's spinning the opposite way, doesn't matter. Always wants to turn clockwise to remain rigid in space if the Earth is moving from west to east. Okay? But how does the gyro know which is north and which is south? How does it know that the orientation of the gyro is north this way and not north this way? Well, they say it's because due to the rotation direction of this. That's how it's determining it. This is the section in the manual where it goes over the operating theory of the gyrocompass. And I'm going to use my super precision gyro again as a visual aid. So let's say that this side is north, this is south. We've got a weight on the bottom here, and we're going to orient it like it's shown on the diagram here. So we're looking at a side-on view. You can see the vertical axis there and the weight on the bottom. So it says, consider the example shown in 2A, which is this, which shows a free spinning gyroscope aligned so that its spin axis is level with the horizon. In this example, the spin axis of the gyroscope aligns with the local meridian so that its north end points north, like this. In the balanced condition shown, the weight suspended from the gyroscope bearings has no effect on operation, and the gyroscope will maintain its alignment with the meridian. Okay, so we're assuming that true north is this direction. So we have it aligned with true north, and in this balanced condition, this weight at the bottom, gravity is keeping it there, the axis is aligned with the meridian, and therefore nothing happens, it just stays nice and level. It says it's more common for the initial alignment of the gyroscope, however, to be at some angle away from true north. So therefore two conditions apply. So first condition is the gyroscope's initially level and aligned to the west of north and then to the east of north. So let's go over the west of north first. So with the spin axis of the gyroscope initially level, but with the north end pointing to the west of true north, the arrangement will briefly be balanced as shown in figure 2a. So we're going to move west of north that way, and initially it's balanced like this. So the gyroscope's not running at this point. It says, however, over time, as in it's spinning, the gyro's getting up to speed, the north end of the spin would begin to tilt downwards, like so. This is because the Earth rotates while the gyroscope maintains a fixed orientation in space. Rigidity in space, right? That's what that's saying. So the reason that's tilting down like that is because of the property of rigidity in space of a gyroscope. So in this off-balance condition, as in shown in 2b, the weight would try to return it to its central location, and in doing so would apply an anti-clockwise torque to the gyro suspension. With the gyro spinning in the direction shown, precession arising from the anti-clockwise torque would move the north end of the rotor eastwards. Okay, so it's saying that this weight on the bottom is trying to pull it down back again level, and in doing so, it's moving this back round to the north until it aligns with the meridian again. Now let's go to the east version. So the east, it's initially lined east of north, which is this way. And this time, it's saying that the north end would begin to tilt upwards with the rotation of the Earth. Again, with the rotation of the Earth, so rigidity in space again. So let's just think about this for a second. If we've got north here, and let's say we just go 1 degree, tiny little amount to the west, what they're saying is that it's going to tilt downwards in that case. And if it's 1 degree to the east, it's going to tilt upwards. But that's not how rigidity in space is supposed to work. It doesn't matter what the orientation of the gyroscope is. It should be the same no matter what. Anyway, if you couple this together with what I was talking about, the damping effect earlier, using that big heavy weight that was on the top of the gyro in the gyro compass, and the elliptical pattern that it's supposed to trace out, I believe that what it's doing is it's doing this, and it's trying to get itself closer to the meridian. Why it stops on the meridian, I have no idea, but I do believe that it is doing this, although it's so minuscule and the reactions within the actual gyro compass occur so quickly you can't actually see it doing this. Anyway, let's go and see what this looks like again on the globe. So, with the spin axis aligned east of north, as the Earth rotates this direction, this rotates in the opposite direction. Aligned west of north, it goes with the spin axis. And I'm deliberately doing it short. In the Leon Foucault type experiment, supposedly, this takes this amount of time to point to north. Whereas in the case of the gyro compass, it does it within under an hour, so it's like doing it much quicker. And of course, when it's aligned east of north, it's doing it much quicker as well, but against the spin of the Earth. So I'm now going to show 3 hours worth of north-seeking tests in approximately 3 minutes, sped up of course to show the movement more clearly. It's worth noting here that the gyro compass works in 2 steps, north-seeking and north-keeping. North-seeking is the first step and is what we're demonstrating here. During this step, the unit must be as stationary as possible to seek true north. It takes between 24 and 90 minutes to find true north, upon which the green ready light comes on and it changes to north keeping mode, and from there on in it can be moved around and used for navigation. So first I used the gyro compass to determine true north and aligned the unit accordingly. I then tested its north seeking function with the gyro axis initially aligned to all 4 cardinal directions. I made a note of the direction it moved and the duration of each test on the notepad at the side. The southern aligned test that you'll see in a few minutes was particularly interesting because if it was indeed aligned exactly on south, then the rotation direction could have gone either way, but on this occasion it decided to rotate counterclockwise against Earth's spin direction. In conclusion, the gyro compass seems to behave like a magnetic compass, although it is not seeking magnetic north, rather true north. If I was to take a bar magnet and hold it on the east side of a magnetic compass, it will hold the pointer to the east. If I take the bar magnet away, it will return to north in a counterclockwise direction, and obviously clockwise from the west. This is exactly how the gyro compass behaves. It does not seem to care about the direction that the Earth is spinning and does not adhere to the notion of rigidity in space, as this would necessitate a clockwise rotation always in the northern hemisphere, with the Earth spinning west to east. We know how the gyro compass works and that this particular unit is functioning exactly as it should. However, what is still puzzling is why it is seeking true north. Why does the y-axis tilt down when west and up when east? I've done some initial testing by entering false latitudes into the unit, and I find it interesting that you need to enter your latitude to begin with. This is true of all gyro compasses, not just this one, so it alone, without intervention, cannot seek true north. And in fact, if I enter a false latitude, it will show an error by as much as 5 degrees off of true north. I do plan to do more testing with the device in the future by entering false northern and southern latitudes, but for now I hope you enjoyed this demonstration and understood the point of the video. That is to say that a gyro compass will seek true north in whichever direction is closest to north, and not always clockwise, as would be the case if it were rotating on a unidirectional body but remaining rigid in space.